start this. A couple of housekeeping things first. I don't know if you saw the note that I changed on Moodle, just in this week's lab section, or kind of the blurb. But I talked to a coworker, Jenna, and she said that she can come in for the 8 o'clock lab, but you're just working on lab 3, so it's really very optional if you want to go in, or if you don't, doesn't matter. But she's teaching some other stats labs, so she'll know exactly what's going on. So if you're working on lab 3, then the labs will still kind of be on. They'll both be in C2 86, 260, I don't know, I can't remember. We're 368, 286, I don't know, can't remember. And I didn't write it down. I put it on Moodle though. Let's see if I can get there. Anyways, so she'll be there for the 9 o'clock block. She actually has a calculus lab in there, but she'll be there to answer questions if you have any. So I really, really doubt, oh, what's this? That's not the one I wanted. I really doubt that it's gonna be a full lab for her anyway. So just go down, down, down. Here, this is me falling behind. What kind of a math teacher doesn't fall behind, right? So I'm just, it's just how it is. 286. So that's where the first lab usually is, just next door to the second lab. Okay? So she'll be there if you want to work on lab 3. If you've already done it, or if you want to do it some other time, that's totally fine. I won't be there. But instead of not hosting any labs, I thought I'd ask her to come in early for us. But I'm sure she's happy to just hang out too. Okay. So I will not be here for labs this week. But Jenna will be in C286 if you have any questions about lab 3. If you have any questions / want to work on, whoops, whoa. Lab 3. Lab 3, remember, is due on February 7th. At midnight, of course, or at 11:59. Okay. So you've got time to do it. Let's see. So we're gonna finish regression today, which is, this is kind of my favorite part of regression, is where we're gonna just calculate the slope and the intercept, because we talked about all the kind of background theory, right? So we've got these residuals, right? So the distance from the actual points to the line, we're trying to minimize that distance for the line of best fit. And so now we're gonna actually calculate this line of best fit, right? And so I'll show you how to do that. We finished off talking about the correlation, right? And so if you don't have, I have some extra formula sheets here. If you don't have your formula sheet, might be helpful to grab one. But so just as a little bit of review, but not too much, right? We talked about the line of best fit, and that it minimizes the residuals, technically the squared residuals, not really that important. We also talked about using the residuals to assess the fit, right? And so today we'll talk a little bit more about the conditions that we're checking. And so we use the residuals to assess the fit of, let's go crazy here, the model, right? The linear model, the line of best fit, right? And so we'll just call it the model, right? We're trying to model the population. Cool. And then we said, well, we can also calculate the correlation between two things, right? And so we can calculate the correlation, which we said was the numerical measure of the strength and the direction of a linear relationship, right? And so we said that the correlation is a numerical measure of the strength and direction of a linear relationship, right? So that's the key, that we have to have a straight line in order to model it with a straight line, and in order to use this correlation that we're talking about of a linear relationship. I'm even gonna underline the linear. Usually that's one of those like kind of multiple choice, like really read it, right? So the correlation, in order to use that correlation, it has to be a linear relationship, right? So you always want to make sure that it says it's for a linear relationship. I don't like those questions, but they happen a lot, right? So something to look out for. We said we can calculate the correlation. The correlation we just denoted by R or lowercase r or capital R. It doesn't really matter. I think what you'll find is that I tend to use lowercase r. The textbook is using capital R. I tried to change, but it's really hard to change something like that, right? So just know that they're the same in this case. So correlation is SXY over SXSY. SXY is the covariance of X and Y. And we said, so where SXY is, and this is on your formula sheet, the sum of your X times Y's, oops. You don't, this is bad for saying this, but you don't actually need the I's, the subscript I's. They're just saying do this for every observation, right? Take X times Y, X times Y, X times Y for every single one. So if you want to just kind of close your eyes to the subscripts I's, that's fine, because I know they're kind of nasty to look at. So the sum of the X times Y. So in your, you'll have your X and your Y column. You'll have to make a new column of X times Y, and then subtract N, which is your sample size, times X bar, which is the average of your X's, over the average of your Y's, over N minus 1. Usually, I'll just give you SXY, right? So you don't have to calculate it. I'll give you the standard deviations, or I might even just give you the correlation, right? And so that would give you, you'll see that that saves you a little bit of time later on, but that's the breakdown of it. So we'll call that the end of our little review here. So when we're fitting a line, right, so we're starting 3.4, which is the actual fitting a line. Fitting a line by least squares regression. Oops. Which we can abbreviate LSR, least squares regression. So what you're going to do, right, is the first thing you're going to do is you're going to make a scatter plot of this relationship, right? And you're going to check some of these assumptions. And so after visualizing the relationship between X and Y using a scatter plot, we need to check our assumptions, right, for the least squares regression line. We need to check the assumptions for the least squares regression line, which I'll just call LSR. The first assumption is linearity, right? We can't fit a least squares regression line unless we have a straight line relationship, right? So the first one is obvious. And so our first assumption is linearity, right? We must have a straight line relationship, right? We must have, I'll just call it a linear relationship. A linear relationship to model it with a line. Hopefully that one feels, yep, that makes sense, right? If you have some sort of curvature, you don't want to use a straight line to model it, right? That doesn't make sense. The next thing we're going to talk about is the residuals, right? So now we're talking about how the points behave around this line, right? So our residuals have to follow a nearly normal distribution, right? So we say that we have to have nearly normal residuals. We don't have the residuals until we fit the line, right? But usually if we look at a scatter plot and we have just kind of even scatter around the line, then we can assume we have nearly normal residuals, right? And so even scatter around the line of best fit usually means we have nearly normal residuals. Usually means we have nearly normal residuals. But what we're going to do is later on, we're going to confirm with a residual plot. Oops. a residual plot puts the residuals on the y-axis, and for this course, we'll put the explanatory variable, or we'll keep our explanatory variable on the x-axis. And then what we're looking for is put a line at 0 here. We're looking for random even scatter around 0. Look for random even scatter around 0. We can also make a histogram of the residuals. We can also make a histogram of the residuals. To check normality. So a lot of things kind of going on with the residuals. But the rest of the assumptions that we're going to check all kind of fall back on the residual plot again, right? And checking these same assumptions, right? Looking for even scatter around 0. And so our third assumption is that we have constant variability. Constant variability. Variability. Variability, right? Think about variation, variation around the line, right? We have to have constant variability around the line, which again, like I said, is just falling back on, well, that means our residuals have to be just kind of randomly scattered, but kind of evenly scattered around the line for all values of x. Okay. So the constant variability says that the variability of the points around the line should be roughly the same for all values of x. Should be roughly the same for all values of x. I'll put a note here, right, that we check using residual plot above, right? Because what we're looking for, constant variability, is random scatter around 0, right? So random scatter around the line. What non-constant variability might look like if we're just looking at our response against our explanatory variable. Say this is our line of best fit. If we have something that looks like, so super tight around here, and then at some point, things kind of get out of control, right? And now we have all this variability. This would be non-constant variability, right? And the trouble with that is it's hard for us to say how good this model is fitting, right? Because what we would have to do is we would have to break it down that for these values of x, right? If we just looked at these values of x, then this model is doing a top-notch job, right? There's very little variation around here. It's capturing all that activity, right? And then at some point, something happens, and for these values of x beyond that point, right? Now all of a sudden things start to go kind of haywire, right? And this line, if we didn't have these points, right, maybe this line wouldn't be like this. It would maybe move around a little bit, and it's not doing a very good job again, right? And so that's why we need to be concerned if we see something like this, and we probably have to do something about it. That's not for this course, right? But for you guys, it's just about recognizing that, hey, that's one of my assumptions violated, right? And so here, this here is non-constant variability. In that residual plot, what you can think about the residual plot as being is the residual plot basically just kind of takes this relationship, puts it on its side, right? And so this line is that line at 0. And then we would be able to kind of zoom in on how these points are behaving around the line. And so the residual plot, I think, confuses a lot of people because they're expecting to see something different than what they saw in the scatter plot. But the only reason we use the residual plot is because it just magnifies that relationship, right? And so if it's not clear in the scatter plot, we look at the residual plot just because we're able to kind of zoom in a little bit, right, and see it closer up. And so for our residual plots, let's see, I tried to have it ready so I can steal it. Oops. This is figure 316 in your textbook. Figure 316. Right. The first line of plots, this is your actual scatter plot. Right. I'll actually move this over a little bit. So these are your scatter plots. And the ones below it are the residual plots. So what you'll see, right, the residual plots just magnify what's going on in the scatter plot. The residual plots magnify the relationship in the scatter plot, right? And that's all they're doing. What assumptions are being violated in each of these? The first one, it doesn't look like we should be using a linear relationship, right? So that's the first assumption, that the linearity is being violated. In the second one, right, we haven't really talked about it, but we've got some outliers, right? So here, if I just kind of assumptions violated. In the first one, it's linearity. The outliers, right, would give us kind of a non-normal distribution for our residuals, especially because we've got that one point that's way above the line on the lower end, right? And so here we would have the normal residuals would be violated, right? Because of this guy in particular. In the third one, right, our constant variability is being violated. In the fourth one, we haven't gotten there yet. It's not always something that you can see in a plot, right? It's not always this obvious, but the last assumption that we have to check is, do we have independent observations, right? And so if we're talking about things like the weather, right? The weather today, it's a little bit dependent on the weather yesterday, right? Sometimes not around here, right? But usually, right, we don't expect tomorrow to walk outside and it's 20 degrees. That would be really strange, right? Because based off of today, we know what to expect sort of for tomorrow, right? And so here, this last assumption is, do we have independent observations, right? And so are all these things independent of each other? Like I said, right, if we have this kind of relationship where they're all kind of just following each other, and sure, we can fit a straight line through there, but it doesn't really capture the actual activity, right? Then here we say that we don't have independent observations, which is our last assumption. Usually for independent observations, right, like I said, we don't always just see it like as clear as that on the scatter plot. But usually we have to argue that it's reasonable to think that these would be independent observations, right? Because they were randomly selected. There's no reason to think that they should be related to each other or the responses should have anything to do with each other. And so our fourth assumption is that we have independent observations. We usually have to argue that our observations are independent of each other. That our observations are independent of each other. Right. If we have some sort of sequential data, right, so non-independent observations, we have to deal with that with different types of analyses, right? And so we're not gonna get there in this course, right? But we would need to, let's say, employ other types of analyses if our data is sequential, right? If they're non-independent. So independent observations are just, usually we need to have a random sample, right? And so independent observations, depending on what I'm asking you about, right? If I ask you, if I'm asking people on campus if they like stats, right? And I go out into, you know, the whole campus and I ask around, hey, do you like stats? Do you like stats? Yes or no, yes or no. And then I come in here and I have an overwhelming yes, right? I can't really assume that you guys are independent of each other because you're all in the same stats class, so you love it, right? Whereas if I'm out there and I happen to pick one of you, that's fine, right? One or two or whatever, as long as I'm randomly selecting, right, then that's usually how I can ensure that these things are independent of each other, right? And so even things like if we're talking about diseases, for example, genetic diseases, if you're sampling siblings, those would be non-independent observations, right? And so we'll talk more about those later. But I will say here, random sampling ensures independent observations. Okay. So those are our assumptions that we have to check. And it's kind of a little bit weird, right? Because we look at the scatter plot and we imagine that we fit a line. And then we do fit a line if the assumptions seem reasonable. And then we go back and we actually check it with the residual plot, right? And so you're not going to go ahead if you don't have a linear relationship, for example. So for us, usually the assumptions are going to be met. It's just a matter of jumping through the hoops of saying, yes, there's linearity. The residuals look like they follow a normal distribution. I have constant variance, and I can assume that I have independent observations. So it's just going to be a hoop that we jump through. All right. Now to actually calculate the line, right? We need a slope and an intercept like we talked about last day. And so I've got a page break here so it won't look so weird later, but for now it's a little bit squished. So calculating the least squares line we said last day that our least squares regression line is going to look like y hat is b1x plus b0. Where y hat, anything with a hat on it in regression is going to be the predicted value of whatever is below it. So this is the predicted y. Whatever is attached to the x is the slope. And whatever is on its own is the y-intercept, which usually I'll just call the intercept, right? It's assumed that we're talking about the y-intercept. What I'm going to do is I'm going to give you the formulas that are on your formula sheet. And even this formula is on your formula sheet. If you look, it says the least squares regression line is y hat equals b1x plus b naught. B sub 0 or b naught, not meaning null, and 0, null, they're all the same. We kind of hinted at it last day, but we like to write the slope first, right? B1, even though it looks like we should be calculating B naught first, because we need the slope in order to find the y-intercept. And so on your formula sheet, you have B1 is sy over sx times r, and B naught is y bar minus B1 x bar. Let's just count how many things we need to know in order to be able to do this, right? We need to know the standard deviation of y, the standard deviation of x. We need to know the correlation, r. Okay. Moving on to the intercept, right? It looks like I need the average of the y's and the average of the x's. But then for the slope, right, which I'm using in there, I would have already calculated, right? So I need 5 things in order to find the slope and the intercept. So we need to know sy, sx, r, y bar, and x bar in order to find y hat equals b1x plus b naught. So in order to find our least squares regression line, usually, right, you'll have everything that you need, right? At the easiest thing is if I just give you those 5 things and you plug them in, and then you just solve it, and then you're done, right? We just, in our review, right, we said that we could run into a little bit of trouble if we don't have the correlation, right? To find the correlation, we need sxy, sx, and sy, right? So the only additional thing that I would need in order to solve for r would be sxy, which is another thing that I would give you, or you might have to calculate if it's a tiny data set, right? I think on one of the assignment questions, 1 or 2, I can't remember, it gives you the sums of the x times y's, right? So you can use that to find the sxy's. But for tests, right, I would either give you the correlation or I give you the sxy so that you can find the correlation. So r or sxy and then you'll be able to use that to find r. Right? But at the top of the level, right, these 5 things are what we need to know. Okay, so let's see what I was gonna do here. Let me steal, where did it go? So, oh, this one first. Okay. I'm going to steal figure 315 and do a little example here. The textbook calls it the Elmhurst data. Just information on a family's income and their the amount of aid that they get for, I think, for university. Let's have a look here. Yeah, gift aid from the university. And so it's looking at the relationship between the amount of gift aid that they get from the university versus the family income, both of which are in thousands for the units. Right? Just ignore the dashed line because that was the one, they do this kind of silly example of, oh, this is what we would do if we fit it by eye. Well, you would probably fit something different if you were fitting it by eye. And so ignore the dashed line and just look at the solid line. And so here, right, we're looking at 50 freshman students from Elmhurst College, and we're looking at the gift aid versus the family income, right? And so it's kind of reasonable to think that the family income would have something to do with the amount of gift aid that they get, right? And so if you're trying to determine which one is the response variable, right, then the gift aid would be the family's income. You can't call your parents and say, oh, we're going to be rich because I got this much in gift aid, right? So now our income is going to go up. Right? It doesn't work that way, right? Or maybe it's going to go down. Bad news. No, we know that they're not going to be related in that way, right? They're going to be related in the sense that the family's income, right, is going to determine how much gift aid you get, right? And so here, this is our response variable, and this is our explanatory variable. That's going to be important, right? Because here, this is our, oops, there. This is going to be our y, and this is going to be our x. Because if you glance back at the formulas, we have to keep track of the standard deviation of y, the standard deviation of x, and the average of the y and the average of the x's. So we need to look on the scatter plot and just make sure, okay, well, my x's are going to be the family income and my y's are going to be the gift aid, right? So I have to keep those separate because if I mix those up, that's going to be bad news, right? It won't make sense anymore. So we have this, just checking our assumptions real quick here. Looks like we can fit it with a straight line and there's no reason not to, right? So the linearity assumption seems fine, right? We have to have nearly normal residuals. We can say there's kind of constant scatter around this line, right? So that would give us nearly normal residuals as well as constant variance, right? So those are the second and the third assumptions kind of checked off, right? And then they took a random sample, it says, right? So income for a random sample of 50 freshman students. And so there's no reason to think that these aren't independent of each other, right? And so that's how we would check our assumptions. Okay. So now if I asked you to make this least squares regression line, I would give you maybe something like, just stealing from here, table 317. This table, right? And here's what I mean by you have to keep track of your x's and y's, right? Because here it tells you that the family income is the x and that the gift aid is the y, right? But that's not always the case, right? Sometimes I'll just give you the scatter plot and I'll give you this information verbally, right? The gift aid had a mean of 19.94 with a standard deviation of 5.46. And the family income had a mean of 101.8 with a standard deviation of 63.2. And the correlation between the two was negative 0.499. Right? So sometimes it's verbal, not as clear cut as this table here, but because I just want to show you how to calculate these things, right? I'm just giving it to you. All right. So if we have to find the slope, that's our first thing that we're going to do. Our slope, remember, is B1 is is it SY over SX times R, or on this table, it's capital R, right? But just remember that they're the same. So the standard deviation of my Y's is 5.46. The standard deviation of my X's is 63.2. Right away, right, I'm dealing with 5 and 63. If I have those inverted, right, that's not good. That's going to give us way wrong numbers. Right? And then times negative 0.499. What do we know about the correlation? Correlation is negative, right? Which makes sense because we've got this kind of downward sloping line here. 0.499 we said was kind of borderline from weak to strong, right? Which kind of makes sense. We've got this pattern that we can see, right? We see this pattern, this downward sloping pattern, but there's a lot of variation, right? It's constant, but there's a lot, right? So our correlation is moderately strong, let's say, right? And you just kind of feel your way to it. So we're a little bit flexible on the 0.5, right? 0.499. Okay. So if we had to calculate this, 0.499 times 5.46 divided by 63.2, and I might have blubbered it here, but do you guys get negative 0.0431? Awesome. 0.9811013. I've got a hang up. I always write out all my decimals, or at least the ones that I can see, right? I understand that it keeps going beyond this on my calculator. And I want you to do the same, right? Because if you're rounding incorrectly, right? At least if you've shown me the original number, then I can be more lenient with the marks, right? If you went to 0.05 or something weird from here, right? That's not very good. Right? So I want to see all the numbers. Once you get in the habit, it's not that bad. Yeah. So usually I would tell you how many decimal places I want. I would kind of go, usually for something this small, I would probably ask for 3 or 4 decimal places, right? And so for 3 decimal places, round to 3 decimal places, for example, and I should have had it in the blurb, right? If we're rounding to 3 decimal places, then we get roughly equal to negative 0.043. Okay. If I've told you to round your answer, you use your rounded answer for the rest of your work, right? Wherever B1 comes up now, right, you just use your rounded answer. And so forget about all those other decimal places, right? Now we use our rounded answer. Okay. So we've got our slope. It's very little, right? It's negative 0.043, fine, okay? So now we can find the intercept. The intercept, right, is B0 is Y bar minus B1 X bar. Again, really important that we don't switcheroo our X's and our Y's. Right? So I'm gonna go back up and steal my X bar, or my Y bar is 19.94. So I have 19.94. minus the slope that I just found. I'm going to keep it as minus and then put my negative 0.043 in brackets. And then times x bar, which is 101.8. Rules of the road here, right? I have to multiply the 101.8 by the 0.043 before I can, well, now I'm going to add it to 19.94. All right, so I have to deal with that multiplication chunk before I can do the addition or subtraction, right, BEDMAS. And so 43 times 101.8, oops, 0.043 times 101.8. I get 19.94, and then subtracting a negative number, I'm going to change to adding it, plus 4.3774. Notice that I used my rounded value for the slope, right? But now I'm going to keep all my decimal places until the very end, right? So whatever decimal places I get out of this, I'm going to keep till the end. And so this is going to be plus 19.94. I get 24.3174, which, if I'm going to round to 3 decimal places again, 24.317 to 3 decimal places. Now we know the slope, we know the intercept. So now we're ready to construct the least squares regression line. This is one of those construct funny questions where you can really tell if someone's been going to class or not, because this is like the easiest part, right? You're just plugging in your beta, your B1 and your B naught, and then you're done, right? But sometimes if I get questions like, what does this even mean? Then I know you haven't been coming to class. So not for you guys, but that's for everyone who's watching the video later. Y hat, right? Just constructing this least squares regression line just means plug in all these values and that's it. Y hat is going to be, well, in general, B1x plus B naught. So in our case, Y hat is B1, which was negative 0.043 times x plus 24.317. That's your least squares regression line, right? Because the whole idea we said was, well, I'm fitting this model so that I can plug in some value of x and get some predicted value of y, right? So I want to keep my x and y open so that I can keep plugging in different values of x and just keep predicting new values for y, right? And so I know some people are bothered by, I want to fill in all the values, right, and get a number. But we're not going to, right? This is the equation of a line. So now we need to be able to interpret this line, right? Or at least interpret the slope and interpret the intercept. Okay? And so we need to be able to interpret the slope and the intercept. So the definition of the slope and how we're going to apply it to interpret it. Well, if I ask you to interpret the slope here, the slope is negative 0.043. But what it's telling me about how x is related to y is that for each unit increase in x, right? So for each additional, I guess, 1,000 in family income in this case, right? Because it's in thousands. My predicted value of y, which in this case is the predicted amount of the gift aid in thousands, right, is going to decrease by 0.043. Right? So in general, the slope says that for each unit increase in x, we expect to see a slope increase in the predicted value of y. Increase, right, is positive. Even if you wanted to say a negative 0.04 increase, I'm fine with that, right? Even though your mind probably wants to say 0.043 decrease, right? But you don't want to have a negative 0.043 decrease because that's actually an increase, right? So you want to be really careful. And so in this blurb, if I ask you to interpret the slope, then the only things that you're going to replace with the actual things from the question is, well, your x, you can replace it with the family income in this case, right? So for each unit increase in family income, we expect to see a slope, which in our case is negative 0.043. And I'm just going to say a negative 0.043 increase, just to keep this blurb the same, in the predicted value of the gift aid. Right? The sentence is going to be a little bit clunky, but if you have this pattern down, right, then you can just replace it with the things from your actual question, and eventually you'll say, oh yeah, well that's just the slope, right? For each unit increase in x, we expect to see a slope increase in the predicted value of y. The intercept, I've got a similar blurb. If we just look at this line, right, the intercept is 24.317, right? In terms of how x relates to y though, right, our predicted value of y would be 24.317 when x is 0, right? And so that's our definition of the intercept, is the predicted value of y when x is 0. Okay. So the intercept is the predicted value of y when x is 0. So same idea here. You might have to reword it a little bit because sometimes it doesn't really make sense. But in this case, the intercept you can replace with the actual number. So I would probably reword it as the predicted value of y, so the predicted amount of gift aid when the family income is 0 is the intercept, which is 24.317. Right? So I would probably reword it a little bit, right? But just keep in mind that the intercept is the predicted value of y when x is 0. Usually I'll follow this up with, is this value meaningful? Right? what I'm getting at here, well, if the family's income is 0, right, is that ever going to happen? I guess it could happen, right? Hard to see. It could be close to, it could be very low, right? But it's not necessarily going to be absolute 0. So you would argue, can X be 0, right? Is it reasonable for X to be 0? Right? If we're talking about things like temperatures, right? If X is temperatures in Celsius, then yeah, for sure, X can be 0, and that's a reasonable value in our data, right? If we're talking about, you know, the square footage of an apartment to predict the price, if there's zero square foot and you're still paying 200,000, no one's going to go for that, right? So that's not very meaningful. That's just kind of the jump in price for a 200. That's a little bit high, but anyways, right? And so we just have to think, well, can X be 0? And that makes it meaningful or not, right? And so here, we need to ask ourselves, if X can be 0, to determine if the intercept is meaningful. Of course, it's meaningful in the sense that it anchors our line and we need it to draw our line, right? But in terms of interpretation, right, is it meaningful? So what we do, right, or what we are doing, right, is that we're using this line to predict values. Right? We need to remember that we built this line off of these x's, right? So the range of x's in our data, that's where our model is valid, right? We can use the straight line. Remember, straight lines go from -infinity to +infinity. We can just keep stretching them out and out and out. And so that's not the problem. But if we're predicting outside the range of our data, right, so outside our values of x's, we need to be careful because then we're extrapolating. Okay? And so extrapolating is when we use our model to predict values using values of x beyond the range of our data, right? And I'll put in brackets the values of x in our data. If we're extrapolating, right, our predictions are not very reliable. And so if we are extrapolating, our predictions are not considered very reliable. There are situations where we understand that that's true, right? And so if we're looking at kids between the ages of 3 and 12, and we're modeling their height against their age, right? We know that there's this linear relationship. They're just growing, 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 kind of constantly, right? And so they're growing. But then if I said, okay, well, now use this line, right, that you fit between the ages of, what did I say, 3 and 12 or something like that? Use that line to predict their height when they're 50 years old. you would say, no, I can't do that, right? Because people stop growing at some point, and so that doesn't make sense. There's going to be scenarios where things like that are happening in your data, but you don't know it, right? And so that's why you have to be really aware that, nope, I built this line between the ages of 3 and 12, so I should only be using it between the ages of 3 and 12, right? Otherwise, it won't really make sense. Okay? And so that's where extrapolating is really bad. Sometimes we have to, right? Sometimes it's our best guess, but we have to mention that, no, this is not very reliable because I'm extrapolating. Okay, extrapolating is bad. All right, let's talk about the strength of our relationship. So the strength of our relationship and basically how good our model is, we usually use R squared to communicate that. So the strength of the relationship will determine how reliable our estimates are. And to assess the model fit, we use the strength. We use the strength, which is the correlation, right? As R squared. Okay, so remember, correlation is from -1 to 1. Squaring it just makes it a positive value, right? And so if we square a negative value, it just makes it positive. And so now R squared is on a scale from 0 to 1, which we can convert to a percentage, right? And so R squared is the percentage of variability in Y that is explained by the least squares regression line on X. That's a long blurb. That's the definition of the R squared. Okay. As soon as you see percentage of variability, you're going to think R squared, right? And so percentage of variability, you can keep going, right? But if you see percentage of variability, you have to think R squared. So if I tell you that 60% of the variability in blah, blah, blah is explained by the least squares regression line on blah, 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 right? You know that the R squared is 60% or 0.6. And so R squared is the same as a lowercase r squared, because remember, they're interchangeable, which is the correlation squared and often R squared often is communicated as a percentage, right? Because it's going to make it a value between 0 and 1. So your R squared is what we use to say if our model is good, right, or not so good. And so a high value of R squared, yeah. So basically, if we've got a lot of spread around our line, and our line, it's fine, but it's not doing a very good of capturing all that activity, then that would be not so, that would be a not so good model, right? If all our points are on the line and everything's kind of happening the way that you think it is using that model, then you have a good model. And so we call it goodness of fit, which it sounds really funny, but so it's a goodness of fit thing that we look at and say, okay, well, this model is actually doing a really good job, right? And if I get a low R squared, then I know that my predictions aren't as reliable as if my R squared was higher. Right? Usually what we do is if we're comparing models, right? Oh, I use this for X here and this for X here, right? Which one has the highest R squared? That's the one I want to use. Right? So a high value of R squared tells us the model fits the data well, and our results, or I'll say predictions, sorry, and our predictions are reliable. Now, I don't want to give you a cutoff because it depends on the scenario, right? If you're expecting there to be a lot of variation, then maybe an R squared of 50% is pretty good, right? If you're expecting things to be very close together, then an R squared of 0.5 is really bad, right? So it just kind of depends on the situation. And so a high value of R squared means that we have a good model fit. Okay? And so we can use R squared values to compare models. Last section in chapter 3, and I know I'm rushing here. We've got to get through this today. Is on outliers. And so outliers are kind of intuitive, right? If we see something that's on the outskirts, right, we would call it an outlier. And so outliers are these extreme values. Okay. So outliers are extreme values. And depending on their location, they might affect the fit of the model, right? They might affect the fit of the model. So let me just go grab figure 320. So if we've got something like this, bless you. We've got outliers just kind of in each of these. So depending on their location, right, they might pull the line towards them, right? And so at the end of the day, we're not going to deal too much with outliers, but what you would do is keeping in mind that you always want to keep as much data as you possibly can, right? So you don't want to just remove things just willy-nilly, right? You want to keep as much of your data as possible. But what you want to do is you want to fit the line with the outliers and then incrementally remove them if there's more than one and see how the R squared is affected, right? And so if we have outliers, I'll put the S in brackets in our data, we want to try to keep as much of our data as possible. Try to keep as much of our data as possible but what we do is, so our first step is fit the line or fit the model with all the data. Two, fit the model incrementally removing outliers. Incrementally removing outliers. Right. Largest one first, then the next one, then the next one, maybe putting them back in. So you're easily making 20 models here, right? So don't be shy, right? But so you're just playing around. And then what you do is you compare your R squared values. Compare the R squared values, right? So your R squared is always going to increase if you remove outliers, right? Because they are going to be having an impact. But if the R squared doesn't change a lot, I would argue just keep that data point in there, right? And so unless the R squared changes significantly, I would argue that we should keep the outliers, potentially plural, in the data. So that's when you're using that R squared to say, well, actually my R squared jumped from 0.3 to maybe 0.7. Yeah, I should probably get rid of that data point, make a note of it in my report, and say I removed this one just to get a good fit for, it's kind of I sacrificed 1 point for the model of the rest of them, right? That kind of thing. Any questions? Regression. We'll touch on multiple regression, but spoiler alert, we can have more than 1x, and that's it. So see you guys on Wednesday.